Good day, everyone. I am Engineer Nashriel Tapayan, and together with me is Engineer Mervin John Tampus. And in this video, we are going to tackle about the research we conducted entitled Investigating the Influence of AI Tools and Technologies on CIT-U's engineering students' perceived proficiency and motivation to learn programming. So here's an overview of our presentation today. So we will start with the introduction, where we will set the stage of our study, and next we will move on to the rationale, explaining why the study is important. Following that, we have our presentation of the problem statement, clearly defining the research questions that we aim to answer. Then we will discuss our methodology, detailing how we conducted our research. After that, we will dive into the results and discussion, where we will share our findings and analyze their implications. Finally, we will conclude with our key findings and conclusions, summarizing the main takeaways of our study. So, the introduction of AI in education is revolutionizing how programming is taught and learned. AI tools offer personalized learning experience that cater to individual learning paces. For example, tools like intelligent tutoring systems and adaptive learning platforms can provide instant feedback and tailored resources to help students grasp complex programming concepts. The integration of AI technologies in education is transforming the landscape of programming education. It presents a promising opportunity to enhance students' programming proficiency and motivation. However, the potential benefits might be balanced with concerns about over reliance on technology, biases, and the impact on social relationships. At Cebu Institute of Technology University, we saw a promising opportunity to enhance students' programming proficiency and motivation through AI technologies. However, it's crucial to balance these potential benefits with concerns about over reliance on technology, biases in AI algorithms, and impacts on social relationships and critical thinking skills. These backdrop sets the stage for our research. So for the objectives of our study aims to investigate the influence of AI on the programming education of CIT-U engineering students, addressing a crucial gap in understanding its impact on student outcomes. The rationale behind the study stems from the significant potential AI tools have in transforming education, particularly in technical fields like programming. However, despite the growing adaptation of these technologies, there is a lack of empirical evidence on their actual impact on students' learning outcomes. This study aims to fill this crucial gap by investigating the perceived proficiency and motivation of engineering students at CITU before and after the integration of AI tools. So, by understanding these impacts, we can provide valuable insights for educators on how to effectively harness AI technologies to improve educational practices and outcomes. The proliferation of AI tools in education holds great promise, but also presents ambiguity and contention regarding their impact on engineering students' programming proficiency and motivation. Our study focuses on 268 undergraduate engineering students at CITU, aiming to measure changes in proficiency and motivations before and after using AI tools. Specifically, we seek to answer the key questions. First one being, how do AI tools influence students' motivations? What effects do AI tools have on perceived programming proficiency? What changes occur in motivation and proficiency with AI tool usage? What AI tools are most commonly used by students? How helpful do students find AI tools in enhancing proficiency? Our research employed a mixed methods approach, combining quantitative and qualitative data collection and analysis. We collected quantitative data through structured surveys that included Likert scale questions to measure students' motivation and perceived proficiency before and after the intervention with AI tools. Additionally, we conducted focus group discussions and in-depth interviews to gather qualitative analysis. The quantitative analysis involved computing composite scores, descriptive statistics, reliability analysis, and paired sample analysis to measure changes in motivation and proficiency. For qualitative data, we use thematic analysis to identify recurring themes and deeper insights into students' experiences and perceptions regarding the use of AI tools in their learning process. These are the research questions that we target to answer using our research instruments. Through these research questions, we are able to come up with a survey questionnaire, which we distributed to CITU engineering students. For our data gathering, we gathered a total of 325 responses from undergraduate students of CIT-U. These students were gathered through stratified random sampling. Shown in this slide is a specific age distribution of our respondents. And also for this slide, we have the respective gender distributions and year level distributions of our respondents. So as you can see, most of our respondents are freshmen and junior college students. This gives us a sign that our data is skewed towards the earlier adopters of programming. It is also worth noting um, what degrees are our respondents under. As you can see in this slide, most of them are BS computer engineering students, followed by engineering disciplines, which are uh, BSCE and BSME respectively. So as mentioned in the previous slides, the initial data set consisted of responses from 325 engineering students at CIT-U. However, in order to focus on the impact of AI tools, the data was filtered to include only those students who reported significant usage of AI in their learning process, reducing the sample size to 268 students. This sample also comprises first to fourth year undergraduate students who have completed at least 1 year programming course. This targeted sampling ensures that the analysis is relevant and specific to the population most affected by AI tools. The survey will be distributed online to all applicants or participants. Instructions will be provided to ensure clear understanding of the questions. The survey consists of 4 sections. The fourth section is composed of homogeneous questions related to students' motivation to learning programming before the use of AI tools. The second section is composed of homogeneous questions as well, relating to students' perceived proficiency in programming before using AI tools. The other 2 sections are just the homogeneous questions targeting the motivations and perceived proficiency after using AI tools. So aside from the Likert scale survey questionnaires, we also have focus group discussions where participants were selected based on their survey responses. These are to represent diverse views. So FGDs have been conducted virtually and in person. To gain deeper insights, FGDs has been conducted with a subset of survey applicants to discuss their experiences and perceptions of AI tools in programming education. Since our study employed a mixed method approach, we expect that there is a quantitative and qualitative analysis involved. So for the quantitative data analysis, we conducted composite scoring, descriptive statistics, reliability analysis, paired sample t-test, and effect size calculation. For the qualitative data analysis, we have the thematic analysis, which is the analysis of focus group discussions mentioned beforehand. Since we have both quantitative and qualitative results, it is important that we relate them into each other to gain better insights. Triangulating the findings from our quantitative and qualitative data, we can provide comprehensive answers to our research questions. This will help us in understanding not just the statistical significance, but also the contextual and experimental aspects of AI tools usage. Our study employs both quantitative and qualitative research methods. We collected quantitative data through structured surveys with Likert scale questionnaires, focusing on measuring changes in programming proficiency and motivation before and after the use of AI tools. We analyzed this data using statistical methods to assess significance and reliability. Additionally, we conducted focus group discussions and interviews to gather qualitative data, which we analyzed thematically to understand the contextual and experimental aspects of AI tools usage. For the quantitative analysis, we computed composite scores by averaging each Likert scale score per respondent. Descriptive analysis, reliability analysis, um, using Crunchback Alpha, paired sample t-tests, and Cohen's d for effect size calculations were performed to evaluate the changes in motivation and perceived proficiency. For the qualitative analysis, we transcribed and analyzed focus group discussions and interview to identify themes, and we integrated both quantitative and qualitative data, which help us provide comprehensive answers to our research questions. So for the first step of our quantitative analysis, we conducted composite scores by averaging each Likert scale score per respondent. As you can see in the slide, From a Likert scale response score, we converted it into a numerical composite score in order to measure it quantitatively. From those responses, we created a summary through the frequency of the respondents, both for motivation and proficiency surveys as shown in the second table. The data shows for the composite scores for motivation that there is a significant increase in the number of students who felt demotivated. So as you can see, that is 63.43%. This shift is concerning as it suggests that the introduction of AI tools may have negatively impacted their motivation levels for a majority of the students. So for the composite scores of the perceived proficiency, we can see that there is a noticeable increase in the number of students who rated their proficiency as above average or excellent, rising from 24.26 to 50%. This suggests that AI tools had a positive impact on students' perception on their programming proficiency. So quantitatively, the post-intervention data revealed a significant increase in the number of students who felt demotivated and a decrease in those who felt motivated. This suggests that the introduction of AI tools may have negatively impacted their motivational levels. Conversely, there was also a noticeable increase in the number of students who rated their proficiency as above or excellent, indicating a positive impact on perceived programming proficiency. So for the key findings of our study, that includes the following. First is there was a dramatic increase in the student motivation post AI tool introduction. This is possibly due to the complexity and overwhelming nature of the AI tools. Second is the significant improvement in students' perceived programming proficiency, with more students rating their skills as above average or excellent. Lastly is the need for further investigation into the introduction and support of AI tools in educational setting. This is to ensure that they enhance rather than they hinder the students' motivations. So these insights suggest that while AI tools can enhance proficiency, their implementation must be carefully managed to avoid negative impacts on motivation. So for the next slides, I will hand over the floor to Engineer Mervin Tampus. Take it away.
Thank you, Engineer Tapayan. Good day, everyone. I'm Engineer Tampus, and I'll continue the discussion about our study. So on the left of this slide, the descriptive statistics show a notable decrease in motivation levels after implementing AI tools. So the mean score dropped from 3.9 to 2.81, and the median fell from 4 to 2.55, indicating a significant shift in central tendency. The 25th and 75th percentiles also decreased from 3.55 to 2.18 and from 4.45 to 3.00, respectively, showing a widespread decline in motivation. The standard deviation increased slightly from 0.8466 to 0.9253, suggesting more variability in scores. So on the right side, the box plot visually compares motivation scores before and after AI tools. Before AI, or before using AI, the median was 4 with an interquartile range or IQR from 3.55 to 4.45, indicating a high motivation. So after using AI, so the median dropped from 2.55 with an IQR from 2.18 to 3, showing a significant decrease in motivation and increased variability. These findings highlight the negative impact of AI tools on motivation levels. So next slide. So let's look at the key findings from our analysis of motivation scores before and after the introduction of AI tools. First, there was a notable decrease in motivation levels with the mean score dropping from 3.9 before AI to 2.81 after AI. Second, the distribution of scores shifted significantly, showing higher motivation levels before AI and lower scores after. Additionally, variability in scores increased with a higher interquartile range and more outliers observed post AI. These results suggest that AI tools may negatively impact motivation, highlighting the need for further investigation to understand the causes and develop strategies to counteract these effects. So for the next, we also had the descriptive statistics on the left for the perceived proficiency scores, which shows a significant improvement in perceived proficiency levels after implementing AI tools. The mean score increased from 3.39 to 3.76, and the median rose from 3.44 to 3.94, indicating a substantial shift in central tendency. Both the 25th and 75th percentiles increased from 3 to 3.33 and from 3.89 to 4.11, respectively, showing widespread improvement. So the standard deviation slightly increased from 0.76766 to 0.837, indicating more variability in scores. So the box plot on the right side visually perceived proficiency scores before and after AI tools, or before and after using AI tools. So before using AI, the median score was 3.44 with an interquartile range from 3 to 3.89. After AI, the median increased to 3.94 with a similar interquartile range, indicating a shift towards higher proficiency levels. These findings highlight the positive impact of AI tools on perceived proficiency. So we also have other visualization or like histograms in the paper, but we only showed the box plot to um, simplify or uh, summarize the results. For the next slide, we also have the key findings for the analysis of perceived proficiency scores of the students before and after using AI tools. So firstly, we observed a significant increase in perceived proficiency levels with the mean scores rising from 3.39 to 3.76. Secondly, the distribution of scores shifted towards higher values, indicating that participants felt more proficient after using AI tools. There was also a slight increase in variability, with the standard deviation increasing slightly, suggesting more varied responses among participants. Overall, these findings indicate that AI tools positively impact perceived proficiency of the students, warranting further research to understand how these tools enhance proficiency and to optimize their effectiveness in educational settings. So, to ensure the reliability of our survey instruments, we conducted a reliability analysis using Cronbach's alpha, which measures internal consistency. This value indicates how closely related a set of items are as a group, essentially estimating the reliability of our survey. Cronbach's alpha values above 0.70 are considered acceptable in the table. Values above 0.80 are good, and values above 0.90 are excellent. So the table on this slide provides a clear interpretation of these ranges. So in this study, we calculated the Cronbach's alpha for both the motivation and perceived proficiency sections of the survey before and after using AI tools. This measure helps us assess the internal consistency of our survey items. The formula for the Cronbach's alpha shown on this slide illustrates how we tested the reliability of our instruments. So for the results, the Cronbach's alpha for students' motivation in learning programming before and after using AI tools were both above zero point 0.9. So these values indicate an excellent level of internal consistency, suggesting that the items in the motivation section are highly correlated. So the table on this slide shows the Cronbach's alpha results, confirming the reliability of our survey instruments. So for the results of the Cronbach's alpha for students' perceived proficiency in programming, they were also both above zero point 0.9. So these values indicate an excellent level also of internal consistency, suggesting that the items in the perceived proficiency section of our survey are also highly correlated. So the table on this slide shows the Cronbach's alpha results, confirming the reliability of our survey instruments. Moment. Okay. So next slide. So now we also had conducted the paired t-tests, which is shown in the table for the results in the students' motivation of learning programming before and after using AI tools. So the paired t-tests showed a significant decrease in students' motivation to learn programming after using AI tools. So the mean motivation score dropped from 3.9023 to 2.8141 with a t-value of 17.316 and a two-tailed p-value of 1.5087e 45, indicating a statistically significant change. This substantial decrease in motivation could be attributed to factors such as the challenges of adapting to new technologies, increased cognitive load, or reduced engagement with AI-mediated learning processes. So the paired t-test results are displayed on this slide. So next slide. Excuse me. So for our hypothesis testing on motivation scores, we set the following hypothesis. So we have the null hypothesis, which states that there is no significant difference in the motivation levels of CIT-U engineering students before and after using AI tools. And also our alternative hypothesis is that there is a significant difference in the motivation levels of CIT-U engineering students before and after using AI tools. So the parity test results for motivation scores showed a significant decrease in students' motivation in learning programming after the use of AI tools, with a t-value of 17.316 and a two-tailed p-value of 1.5087e45. Since the p-value is much less than 0.05, we reject the null hypothesis, concluding that there is a significant difference in motivation levels before and after using AI tools. So next slide, we also have the table for the pair t-tests for students perceived proficiency in programming before and after using AI tools. So the parity test revealed a significant increase in students' perceived proficiency in programming after using AI tools. So the mean perceived proficiency score rose from 3.3864 to 3.7595 with a t-value of negative 8.0954 and a two-tailed p-value of 2.0347 E14, confirming the statistical significance of this change. This increase suggests that students felt more proficient in programming after using AI tools, potentially attributed to enhanced learning experiences, improved understanding of programming concepts, or the supportive nature of AI tools in facilitating programming tasks. So the paired t-test results for perceived proficiency of the students are displayed on this table, on this slide. So now we proceed for the hypothesis testing on the perceived proficiency scores. So in this testing, we have the null hypothesis, which states that there is no significant difference in the perceived programming proficiency of CIT-U engineering students before and after using AI tools. For the alternative hypothesis, there is a significant difference in the perceived programming proficiency of CIT-U engineering students before and after using AI tools. The parity test results for perceived proficiency scores indicate a significant increase in students' perceived proficiency in programming after using AI tools, with a t-value of negative 8.0954 and a two-tailed p-value of 2.0347e14. So since the p-value is much less than 0.05, we also reject the null hypothesis, concluding that there is a significant difference in perceived programming proficiency before and after using AI tools. Now I'll hand it back to Engineer Tapayan for the discussion of the effect size calculation and thematic analysis.
Before concluding from the results, it is crucial to understand why testing the effect size is an important aspect of our study. So effect size measures the magnitude of the difference between groups, providing a more nuanced understanding than p-values alone. While p-values indicate whether an observed effect is statistically significant, they do not reveal the size of the effect. In our study, we use Cohen's d to calculate the effect size for changes in motivation and perceived proficiency. This statistical measure allowed us to quantify the impact of AI tools on these variables and draw more informed conclusions about their educational implications. So here are the results in tabular form for our analysis on students' motivation in learning before and after using AI tools. Notice that the calculated Cohen's d value is 1.23, which indicates a large effect size. This suggests that the use of AI tools had a substantial negative impact on students' motivation. Such a large effect size underscores the need to carefully consider how AI tools are integrated into our curriculum in order to avoid demotivating students. So conversely, here are the results in tabular form for our analysis on students' perceived proficiency in programming before and after using AI tools. So notice that the Cohen's d value was negative 0.46. So this indicates a medium effect size. Although the negative sign might seem counterintuitive, it reflects an increase in proficiency as the higher post-intervention mean indicates improved perceived proficiency. So this medium's effect size suggests that while AI tools might challenge student motivations, they also enhance their perceived proficiency in program. So in general, these contrasting results highlight a complex relationship between motivation and perceived proficiency when using AI tools in education. While students feel less motivated, their perceived proficiency improves, indicating that AI tools might be effective in skill development, but not but need better integration strategies to maintain or enhance their motivation. So moving forward with the qualitative analysis, we transcribe and analyze focus group discussions and interviews to identify key themes. Integrating both quantitative and qualitative data helped us provide comprehensive answers to our research questions. These focus groups were subsets of our sample data, which have shown a positive relationship towards AI tools. The thematic analysis was conducted on a subset of our survey respondents to gain deeper insights into the impact of AI tools on programming students. From the initial 268 respondents, a sample of 100 participants who reportedly had positive feedback regarding their motivation and proficiency in AI tools was selected. So this targeted approach allowed us for a focused examination of the experiences and perceptions of students who have actively benefited from integrating AI tools into their programming practice. So the analysis aimed to uncover the key themes and detailed insights into how these tools influence their learning processes and outcomes. So these are the key findings from our thematic, as shown in the current slide. So these diverse findings provide a rich, contextualized um, understanding of how AI tools positively influence student learning processes and outcomes in programming. So they highlight the practical benefits of AI tools, suggesting that while these tools can somehow demotivate students, um, they still significantly aid others in mastering programming concepts and improving their efficiency and programming skills. So I guess that is pretty much all for my discussion, and I will hand over the next slides to Engineer Mervin again. Thank you.
In conclusion, this study found that AI tools significantly enhance students' perceived programming proficiency while simultaneously decreasing their motivation. These findings indicate a complex relationship between the use of AI tools and students' outcomes. Educational strategies must be developed to mitigate the negative impacts on motivation while leveraging the benefits for proficiency. Further research is warranted to explore the underlying factors contributing to these changes and to develop interventions that support both motivation and proficiency in programming education. So, for our recommendations, first, future studies should consider expanding the sample size to include a broader range of participants across different institutions and geographical locations, providing a more comprehensive understanding of the impact of AI tools on a diverse student population. Implementing a longitudinal study designed to examine the long term effects of AI tools on programming proficiency and motivation can help identify trends and changes over time, offering deeper insights into the sustained impact of AI integration in education. So, incorporating a variety of data collection methods such as classroom observations, digital learning analytics, and peer evaluations, in addition to surveys, focus groups, interviews, what we did in our study, these can enhance the robustness of the findings through data triangulation. Further research should also explore the impact of specific AI tools and their distinct features on student outcomes, comparing different AI tools and their functionalities to identify which tools are the most effective in enhancing programming proficiency and motivation. So, investigating the role of instructor support and guidance in the effective use of AI tools is crucial for understanding how educators can facilitate the integration of AI tools in programming education. So additionally, conducting detailed analysis of individual differences among students, such as prior programming experience, learning styles, and cognitive abilities, can help identify how different student characteristics interact with AI tool usage and affect learning outcomes. So delving deeper into psychological factors such as anxiety, self-efficacy, and cognitive load, which might influence students' motivation and proficiency when using AI tools, can help design interventions to mitigate negative impacts. Examining the effectiveness of various pedagogical strategies in conjunction with AI tools can provide insights into the most effective ways to integrate AI into the curriculum. Furthermore, assessing the cost benefit ratio of implementing AI tools in education is important, as analyzing the financial and resource investments required versus the educational benefits can provide a more holistic view of AI tool adoption. So, engaging students as active participants in the research process is also recommended, as their feedback and insights can help refine the study, design, and ensure the research addresses their actual needs and experiences with AI tools. By incorporating these recommendations, future studies can build on the current findings and contribute to a deeper and more nuanced understanding of the role of AI tools in enhancing programming education, ultimately informing best practices and guiding the effective implementation of AI technologies in educational settings. So that will be all for our study. So thank you very much and have a nice day.